Hello everyone, this is the third problem from INMO 2020. So basically a number theory problem states that let S be a subset of 0 to 9. Suppose there is a positive integer n such that n greater than n. Uh, Suppose there is a positive integer n such that for any integer n greater than n, one can find positive integers a, b so that n equal to a plus b and all the digits in the decimal representation of a and b are in S. Find the smallest value of mod S. So this is the problem statement. The subset of 0 to 9, 0 to 9, and we want to find what is the smallest such possible subset S. So first of all, we try to deduce some things. So suppose n equal to a plus b, and suppose this is a, and suppose that the last digit of a is a1, and suppose this is b, some number. We are adding them, and suppose the last digit is b1, and see, n can be anything, okay. N is greater than n, so we are allowed to choose n, but n can be anything. So the last digit of n can also be anything. So suppose the last digit of n is say n1, okay, and n1 can be anything. So n1 can be congruent to the set 0 to 9 mod 10, which means that basically the last digit could be anything. Uh, so the also note that n1 is congruent to a1 plus b1 mod 10 because only a1 and b1 influence n1. So this basically gives us that a1 plus b1 cover all values from 0 to 10, 0 to 9 basically. So what this basically implies is that our set S, okay, the elements of our set should be able to produce any number given. So suppose S we take, and S should produce any number we want. Any number we want. So suppose 12 elements of S are S1, S2. So all numbers from 0 to 9 can be written as Si plus Sj. Cover all numbers. All digits, I should say. Yeah. So this already gives some bounds on S. So suppose S has n elements. Mod S equal to n, suppose. So what is the total number of different digits here? So the total number of digits, so suppose n, so this is basically s1, s2, sn. So we can choose some two of them, which can be done in n choose two ways, or we can choose the same element twice, so n ways. This is the total number of distinct two sums. So to Si plus Sj, either I and j are different in which they fall into this category, or they both are same in which they fall into this category. So nc2 plus n is the total number of combination, and this should be greater than equal to 10, because if they are less than 10, then 10 distinct remainders are only not possible. So this, if we solve this, n is greater than equal to 4, this gives, because 4c2 plus 4 equal to 10, so n is greater than equal to 4. So we know that mod s has to be greater than equal to 4. So let's try for 4 this time. So I will show by a series that 4 doesn't work, because I will show that 4 doesn't work. So if 4 are there, then nc2 plus n equal to 10, which implies that because of this equality, we get that all possible si plus sj are different, because see, there are total of 10 different si plus sj, okay, and we need 10 different remainders. So if there are 10 different si plus sj and 10 different remainders, so si plus sj is distinct for each and every possible I and j. So si plus sj So basically, suppose this set becomes S1, S2, S3, and S4. So every possible pair gives a different remainder modulo 10. So what are the distinct modulo remainders? 2s1, 2s2. Let us write some of them. 2s3, 2s4, s1 plus s2, s1 plus s3, s1 plus s4, and s1 plus, sorry, we are over with s1, s2 plus s4, s2 plus s3, and s3 plus s4. These are the 10 possible 10 different 10 remainders, and all 10 of them are different as proved earlier. So notice that these four numbers already gives four even numbers. Okay, so these four are already even numbers because they are divisible by 2, and from 0 to 9, these all numbers cover from 0 to 9. So from 0 to 9 there are total of five even numbers, which are 0, 2, 4, 6, 8. These are five even numbers, so four of them are already covered here. So one of the numbers here is even. So suppose s1 plus s2 is even without loss of its generality. So s1 and s2 have the same parity. So s1, I will write this double arrows as same parity as s2. Okay, so s1 has the same parity as s2, and notice that any two of them here, these five numbers here have to give odd remainders because even remainders are already covered from the first five numbers. So these all numbers, these all sums have to give odd remainders. So all of them have different parities, which implies that S1, suppose for example, this has parity, suppose odd, S1 and S2 are both odd. So S1 has different parity from S3, which implies that S3 should be even. S3 is even, and S1 has different parity from S4, so S4 is also even, which implies that S3 and S4 have same parity. But this is not possible because S3 plus S4 gives an odd remainder. So basically, what I'm trying to say is that from these five numbers, which we have excluded, at least one of them has to be even. Otherwise, these five different parities cannot hold simultaneously by pigeonhole principle. I showed one of the cases here. So 4 doesn't work because five even numbers, I mean, mod s equal to 4 is not possible because these five odd numbers are already done, and these out of these five, at least out of these five numbers, at least one of them is even. So we get total of six evens, so which implies two of the numbers have same remainder, which is not possible because all 10 of them give different remainders. So mod s is not equal to 4. Now let's try mod s equal to 5, and I claim mod s equal to 5 works. How does it works? So take the five digits 0, 1, 2, 3, and 6. What are the set of remainders? See, 0 can be, what are the set of remainders? First of all, we must check that all 10 remainders are covered because that is a necessity of the set. This set has to cover all 5 remainders, otherwise all 10 remainders. Otherwise, this statement would be violated as I showed here. So uh, 0 can be written as 0 plus 0, and this elements give 0 plus 0, and 1 can be written as 0 plus 1, 2 can be written as 2 plus 0, and 3 can be written as 3 plus 0, 4 can be written as 2 plus 2, 5 can be written as 2 plus 3, 6 can be written as 6 plus 0, 7 can be written as 6 plus 1, 8 can be written as 6 plus 2, 9 can be written as 6 plus 3. Notice that all these numbers in the right hand side belong to the set mod s. Like this is the set S. So all these numbers in the right hand side belong to S. So all the different remainders are covered in S. So this was the necessity condition. Now let's show how every single number can be written as elements in S. So suppose we take, I will show this by an example. Suppose n equal to, suppose nk minus 1, n2, n1, and these are basically digits. For example, if n equals to 1972613 4, so these are the digits of n. So what we do is basically we step by step generate digits. For example, 4, by our set 4, how do we generate 4? 2 plus 2. So 2 plus 2, we write 2 here and 2 here. So a equal to this, b equal to this. Then we try to generate 3. How do we generate 3? 3 plus 0. So we write 3, 0. Then 1. How do we generate 1? 1 plus 0, 1, 0. 6. How we generate 6? 6 plus 0. 2. How we generate 2? 2 plus 0. How do we generate 7? We generate 7 using 6 plus 1. How we generate 9? We generate using 6 plus 3. How we generate 1? Using 1 plus 0. So if we add both of them, we will get n. This is basically n equals a plus b. So this is how we write n as a sum of two digits. So basically, if we write this nk, if we formalize this, if these are the digits of n, so what we do, we write n as a1 plus b1, yeah, n2 as a2 plus b2, and we go until nk is ak plus bk, and notice that all the digits can be written as ak plus bk, because we have showed that any digit can be written as two digits from our set S. So we can add both of them and get the number n. Okay, so any number n can be generated from this set S, because every single digit only can be generated. So we first generate a digit and then we place it. So this was the solution. Mod s equal to 5 works. So mod s equal to 5 is the lowest value, because mod x equal to 4 doesn't work. Mod x equal to 5 works. So this was the solution. Thanks.